I'm already cooking. Just come into this room. Huh? Homework. You can pick it up at the end of the class. So. Okay. Well, welcome to 240. So first, I just mentioned homework number 1 is back graded. And then the other thing, I recently was complaining or telling one of my colleagues that it was so hard to keep you awake. And I guess the extremely high temperature in this room is probably one culprit. The other thing is that we either are digesting or longing for lunch or so. Anyways, I mean, he told me about a ruse or idea or whatever he's using. He in his class, 5% of the grade. So that is basically whether you get an A or an A minus or something like that, right? So if it's not really the course grade, but a little bit the rounding, right? Is for course participation. So I'll try this too. Okay, let's try this. So course participation is 5% of the course. I'll post a new formula on how I'll use it then. And for me, the challenge is going to be that I need to know you, and I'll bring my camera next time, but I forgot it this time. And for you, well, the challenge is that you got to stay awake, right? You got to think this through and stop me and slow me down if it either gets too hot or the material makes no sense. All right? Okay, so with that, do you have, maybe you have better ideas on how to do that. I kind of puts me almost asleep myself. So I want to somehow fix this. It's okay? Let's try this. Then, are there questions, things that you want to participate right away? Okay, so we're talking about noise. And want to finish up that chapter. Of course, noise is something that permeates all circuits, and now we kind of put the plumbing together so that afterwards we can talk about a whole catalog of issues, stability and speed and power dissipation, so on in our circuit. And noise is just going to be one of them, so we need to understand the noise part. If you just frame kind of this thing, all right, good. Well. All right, actually, let's start with this. So the title here is Big Noise Example. Well, it doesn't look all that big, but in fact it is. If the first stroke, and I mean, there are really two important things when we analyze a circuit. First of all, we have to set the right question. Just what exactly do we want to know? Because if we don't focus, we end up with equations that are about as long as the P-Sims 3 equations, and they're not going to tell us anything, right? So that's the number one thing. We have to set up the problem right. And then we have to mill through it, right? And that's algebra, and it's boring and fine, right? So that's the easy part, actually. And then afterwards, we got to interpret our results. And so that's what this example is about. Half of the setup I've actually done already. This is a circuit that has only 2 transistors and looks very simple. But what it really is that we want to build a gain stage. And the way we build a gain stage is we build some kind of an amplifier, an operation amplifier, so. And then we are using, and I've mentioned that already, and we'll see more reasons why we do that, usually passive feedback. And now also it's usually we of course have a differential input. We have often, most of the time actually, we also have a differential output. So this is kind of V in, and this here is V out. Now I need just a tad less zoom that it fits on the screen. Oh, you have a different screen. I look at my small screens and I just okay, just yeah. No, not so. It needs a very fine hand on that thing. Okay, so and then the gain between here and here is set by the ratio of these capacitors, right? Okay, and now of course this circuit, as shown, it doesn't quite work because the capacitors, the charge on these capacitors never initialized. So in practice, in the homework I told you to use a big resistor. Well, in practice you know now, you can't make that resistor, so a big resistor is probably not the thing. So in practice we usually use some kind of switches that actually at the frequency of the clock, that may be 10 megahertz, or maybe 100 megasample A to D converter. We open and close these, and so we first reset, dump all the charge, then we acquire a new signal here and run it as an amplifier, and then we reset the thing again. So all of that stuff is in here, and then inside here there is it is an amplifier, and it's got a differential pair. It's got that has a tail current source. It's got a load current source, and so on. But when I just want to know the noise, well, I don't want to load myself up with how do I build this current source and all of that biasing stuff, how to set this level, how to make the switches and so on. I zoom in on just what produces actually the noise, right? And so what this thing is really is a half circuit model of the part of the amplifier that is determining most of the noise performance. Okay, right? And so that's what we're going to analyze, and you will see that this is just about as complicated a thing that we can analyze with pencil and paper. So later, when we have more complicated circuits, we will do this over and over. That we will figure out what we want to know, and then we capture the part of the circuit that we really need to analyze in order to understand that phenomenon. And sort of in the end, we of course piece the different answers together. So let's go over this big example with that premise. So what is left here? Well, this thing here is just a feedback loop. It models actually this feedback. There is one more capacitor. It's this one. I call it CP. Well, that's the CGS of M1 plus possibly other capacitance that's present here. So that would be a capacitor that goes here to ground, right, and here also. And of course, you kind of may wonder, well, why does he include this and not another thing? Well, sort of obviously there is some experience. I've gotten into trouble because of these capacitors before, and so I know not to ignore them anymore. Right? Notice also that it's one of these types of feedback loops, which is kind of feedback, but not all feedback. Right? This is the feedback loop, but this is really also part of the circuit. Right? So the gain from here to here is not 1 over F, or not 1 over the feedback factor, right? Okay? So we looked at this before and said that this is actually a case where the noise can be amplified because of the feedback. Well, and that's precisely so. And in fact, increasing this capacitor here will increase the gain from here out. So the input referred noise of the circuit increases. I increase this capacitor. Whereas the closed loop gain is just set by these two capacitors. It doesn't change, right? So making this big, noise doesn't go down. It becomes a big problem. Okay, so then this is the transconductor. Normally this would be 1/2 of a diff pair, but here we show only this transconductor. And then often we want more gain, and in this amplifier was the case too, so we use a cascode. So I have a cascode here also. The current source, of course, if it comes to noise, the current source, certainly it will also contribute noise. But I kind of can do that separately, right? That just contributes also noise to the output, and I can add the two contributions together later. Later we're going to analyze current source and noise of those also. So do it one at a time, otherwise it gets just too. Now they have. Well, if it gets too noisy, maybe close the door, even though the temperature may cook us. And then we cannot sleep because it's too hot. Right? Okay, so so what do we want to know? Well, we want to know how much noise comes out of this thing. So for that, we have to draw the small signal model. Now, I'm very lazy. I haven't done this here, or at least I haven't drawn it here. But in practice, you probably will have to. Right. You'll have to do that yourselves. Then we have to identify our noise sources here, relatively straightforward. It's M1 and M2, right? Actually, can somebody go and tell them to quiet down a little bit? It bothers me more, perhaps, than you. I should realize that. Okay, and then the other thing is sort of in the circuit. Okay, oh, that's even better. Okay, so in the circuit, right, if we had drawn the small signal model, of course, we would have here all the parasitic capacitors of these transistors. Well, instead of drawing each of them separately and ending up with whole collections of terms and so on that easily get lost, I often, as I've shown here, lump all of these capacitors into the few most important ones, or most significant ones. Now it's just their ghost. Huh? And then the other thing is, well, it turns out that the sort of what's happening here really depends largely on high frequency behavior. Why? Well, because open loop, that is, without this feedback loop here, this capacitive feedback loop applied, the circuit's response, and consequently also its ability to amplify its own noise, something like this. This is very high gain here, and then there is some kind of a unity gain frequency. So there's frequency, and that's... Thank you. I'm sorry to bother you with this, but I guess you fixed the problem. But then we have feedback, and let's assume here two things that I haven't stated on the paper, but we assume, we just assume here for one, is that the circuit is stable and that we have relatively good loop gain. So closed loop, the gain of this circuit. Let me try to use color. Okay. Closed loop, the gain of the circuit is something like this. So all of this extra gain here, it's important in order to make the circuit be accurate, right, and linear and all of that stuff. But it really doesn't affect sort of the noise performance, for example, very significantly. It doesn't affect the speed of the circuit. What does this mean? Well, it means that we probably can safely neglect all these ROs in the transistors. And if we can do that, heck, I mean, it makes a big difference. Just write down the equations with these things and then try to solve them and then without. And you will see right away, I mean, you save yourselves an hour. And probably 3 mistakes that you may or may not find. Now, obviously, things like that, there is always a little bit of a danger when we make such a postulate or such assumptions or such conjectures, right? We might be wrong. So that's why we have SPICE. We simulate afterwards with SPICE, and if we see, gee, I mean, this doesn't agree at all, then we go through and, well, what kind of assumptions have we made? And maybe we find one that is particularly suspicious. And we go and try to modify our result and, well, pay the hours of extra math to deal with them. But it's good to start out with reasonable assumptions, and, well, we can always go back and fix things if it turned out we were a little bit overzealous. All right, so then here is exactly the same example again, so it doesn't matter that it's too small to see. The next thing, now comes the mechanics side. So now this trivial stuff. I find my nodes, nodes of unknowns. Here we have 3, V out, and then 2 intermediate nodes here. And the input noise, we kind of know. And in here, and again, I mean, I didn't draw the small signal model, but sometimes you can do it in the large signal model, and sometimes you just do it in your head. And most of the time, and like in the exam, when you really want to get the right result, you actually draw it the old-fashioned way. And so I put my noise current sources here in parallel with the drain and source of the transistors. Okay. So then, now, the first thing is I get to calculate all the transfer functions from the noise sources to the output, and possibly I need also the transfer function from the input to the output. So I write equations, one equation for every one of these nodes, and then I solve them. Now already here again, this thing here is just a capacitive voltage divider. course, it makes our equations a lot simpler if we just write the equation for a capacitive attenuator, basically, and then capture the attenuation factor in just one single factor. Again, the equation gets shorter and consequently easier to solve. So then, from solving this equation, so V out equals a function of these two noise currents. That's just pure algebra. So we're not going to do this here. I've done it, and you can try your hand at it yourselves. And here is the result. Now, I've already done a little bit of pre-work on this result, right? I didn't just write down an ugly thing with terms all over, but I actually grouped the thing a little bit. I grouped it into, this part is most recognizable. This is really the frequency response part of the thing, right? Apparently, this thing is a second-order low-pass filter, right? At low frequency, S equals 0. This part is just 1, and then at higher frequency, it's going to rule off, right? And at very high frequency, it's going to go to 0. Okay? So with that part, and then this is sort of the constant gain factors, and of course the inputs. So there is the noise current from M1, and that just gets amplified and then low-pass filtered. There is also the noise current from M2. And interestingly enough, that noise current looks, at the output of the circuit, looks quite different. In fact, it gets filtered, it gets high-pass filtered, this thing. At low frequency, M2 contributes no noise whatsoever. Now, this is, what I just said is not exactly correct, and the reason I made that mistake is that we neglected OR out. If we were to introduce all these OR outs, then you would see that at low frequency, the noise contribution of M2 is perhaps 1% of the noise contribution of M1, but it's not 0. Good enough for our analysis. Okay. And then at high frequency, of course, it's going to go through the roof, and there is sort of a critical frequency, omega p, when both noise sources contribute equally to the output. Of course, it could be the dimension transistors M1 and M2 different, and frequently we do that. Frequently we'll actually use a larger, we'll use a smaller V star on M2 because it reduces sort of the amount of voltages needed, and the noise isn't that big a deal because of this high pass factor. Okay. And then there are all of these things. So in here are really two frequencies. One of them is omega u, and one of them is omega p. Again, I've given them names. So let's try to understand what these really are. If we pull this thing apart, and again, I invite you to, when you do the homework, so when you do anything that is a lot of work, do that also. Pull your result apart, interpret it, figure out whether you couldn't have gotten that more easily, or whether you cannot intuitively understand what's going on. So it's again log frequency, and here's sort of frequency. If you can adjust it dynamically without me asking, hey, hello, this guy's really sleeping. Can you, not without me saying, just adjust it a little bit when it doesn't fit on the slide? Thank you. Okay, so so there are really, if we had analyzed the, even the open loop frequency response of this thing, we would have found that at some point we have a unity gain frequency, FU open loop, right? And then at a higher frequency we get a pole frequency, omega p. And this omega p actually is contributed by the cascode, and the cascode contributes a pole. You probably calculated that in 140, and maybe you looked at the result and then you remember and know that it's GM2 over the capacitance at the cascode. So that also came out of the analysis that we just did. Okay, and then we closed the feedback loop. Oh yeah, it is new. Okay, and when we close the feedback loop, really at low frequency, we get this, and then Goes off like this. Now this is, I sometimes use the omega, sometimes I feel, there's 2 pi in between. So here we have omega u closed loop. Okay? So not too surprising, yeah, I mean, we get these poles, right? We get the closed loop bandwidth of the circuit that is somewhat stepped back, actually just by the gain of the circuit stepped back from the unity gain bandwidth of the open loop amplifier. And then we have a non-dominant pole here that's contributed by the cascode. Now where this non-dominant pole is, heck, I mean, it depends on how we design things, but because we want to build feedback circuits that are stable, and we have postulated here that we designed a feedback circuit that is stable, we know that the non-dominant pole kind of got to be at a reasonably high frequency, as I've plotted here. Right? Okay, so now this goes back by the amount of just by the closed loop gain, which happens to be 1 over f. So this frequency here is just equal to f times the unity gain frequency. Let's say omega u open. Right? That's what this frequency is. And if you go back here, that's precisely what all these equations tell us. It tell us, okay, I mean, we have 2 poles now. You need a little bit more zoom again. We have, thank you. Okay. Yeah, I mean, we get 2 poles, but in reality they're probably going to be split apart, and they have frequencies omega u and omega p. Right? And omega p is a fairly high frequency, and omega u, well, that's the bandwidth of the closed loop system, and it is f times Gm over CL. Gm1 over CL, well, that's just the unity gain bandwidth of a common source stage. So that's exactly what we expect from this transistor. It's the unity gain frequency, right? It's a common source stage. Okay. The only thing is that the load capacitance is a little bit different. Well, we get CL, that is the load that we have at this node here. There is a cascode that goes through it, but there's this load. And then we also get some of CF that is also connected to the output, and therefore loading our circuit. But we don't get all of CF. Why not? Well, because we have Miller effect. When this goes up, then this node also goes up by less, and the factor between here and here I've defined as F, right? So it makes perfect sense that we get only a fraction, 1 over F, times this capacitor CF. Okay, so actually these equations, they all perfectly make sense, and probably with hindsight, it was a waste to write down all the equations. It probably could have written this down by inspection, but only with hindsight. Okay, so now let's look at the noise again. So here what I've done, thank you. Here what I've done is I've again reorganized my equation, but now I've made it that now I actually plugged in the noise contributions for KT, gamma, GM for the transistors, okay? And so that's what I get here. Then I did another little thing. I made it that, so here we again have our transfer function that I now had to square because now we're in the power domain, right? But then that's the noise from the individual transistors. And I formulated my equation carefully that this is the noise contribution from M1, and this is the noise contribution from M2. And I scaled things such that that M1's contribution really is pulled out to the front of the equation, and so I have a factor unity appearing here, and then this is the relative noise of M2 compared to the noise contribution from M1. Okay? And so this again confirms our earlier result. At low frequency, well, S is 0, M2 just plain doesn't contribute any noise. But it also tells us that at high frequency, somewhere around this frequency omega p, the noise contribution from M2 can become significant. And the ratio of GM2 and GM1 plays in here. We don't know what that ratio, or I haven't specified what ratio we're using here, but both transistors run the same current. So the only way to give them different GMs is really to give them different V stars. Well, we know that one transistor could have a V star of 100 millivolt and the other one 300 millivolts, so vice versa. So a factor of 3, within a factor of 3 to 5, these GMs actually are probably going to be equal, right? So really, around omega p is where suddenly the noise from M2 should matter. Omega p, what frequency again is that? Yeah, and you should use the microphone, please.
It's the frequency of the second pole, the non-dominant pole.
Right. It's this non-dominant pole, and it has it's of this form, GM2 over Cx. Actually, do you know a name of this frequency? Another name. If you go a little bit back to when we talked about devices and device figures of merit and stuff like that. Omega t, yeah, exactly. Look at the circuit again. Cx here, that's the capacitance hanging at the source of M2. Well, really the capacitance at the source of M2 is the CGS of M2 plus junction capacitance, the CGD, right? CGS is a significant part of that. Maybe half, maybe even more than half, sometimes less. Depends on the layout and so on. Well, so GM2 over Cx is really GM2 over CGS times CGS over Cx. And CGS over Cx, I just argued, is something like 1/2 or so. Right? So this omega p here is really about omega t of M2. And we've seen omega t. What is sort of a reasonable number for omega t in our process? Yeah? Yeah, sort of gigahertz, right? A gigahertz, maybe a little bit more. If we were in a shorter channel length technology, it definitely would be more. It would be maybe 10 gigahertz or even more if we tried to make it high. Right? So gigahertz is a good order of magnitude. So very often, I mean, we built something that runs down at a few 10 megahertz, or maybe even a couple of hundred megahertz. It's fast, but compared to omega t, it's not that fast, right? So we may not need to worry about this. Well, before we make too big statements, let's just calculate what the noise contribution is from M2. Okay, and we calculate this now in a different scenario. We calculate now the total noise at the output, right? We sort of get into this game of our amplifier ultimately is driving an A to D converter and so on. And again, I've argued that even if that's not the case, we very often use that. So basically what I'm saying is that our amplifier with its capacitive feedback network and probably some switches to make it work. Now, again, I just draw this, the half circuit. It's really in a configuration like this. Right? So we amplify the input, and then through a switch, we charge up the capacitor, and then we open the switch, and we get all noise aliased onto CL. Again, here in this circuit, kind of it's obvious that we want the on resistance of this switch to be fairly low. Why? Because otherwise we have no chance that the signal is going to actually settle onto CL. Okay, and so then the sampled noise is going to be wide. Right? That's the argument that we made last time. Okay, so now let's calculate this total noise. Well, that's where we had the equation from before. A little bit more zoom. No. Okay. So the equation that we had already, then we need to integrate that from 0 to infinity. And So here now it pays that we wrote this into a sort of a reasonable form, right? Because now we can recognize this thing is in that table of integrals that I've given you, and even s over this thing is, or s squared over this thing is in that table. And then we just have to add two contributions together. Again, this is all algebra. And here is the result. So this is that total noise. And look at this. It's Kt on C. The C is the effective load capacitor. Okay, so noise-wise, actually, CF, it loads our circuit, but actually reduces the noise a little bit also. Okay, and then there's this gamma, and 1 over f is gonna increase is a part of our noise. So we want this f to be very big, usually called feedback factor. We want this feedback factor huge so that the noise is not gained up like crazy. Now, let's look at the equation again for what that f was. F is this thing. The feedback, it's the feedback capacitance divided by the sum of all the capacitors that are connected to this terminal of our amplifier. So that's the feedback capacitor itself again. Then the sampling capacitor, CS, and it also CP, that is CGS of M1, right? Plus maybe others. So that actually also, so if we want to make this big, then basically we want to make that CF is large compared to CS and CP, right? That's interesting because in our feedback network, I mean, the feedback network sets the ratio, sets the gain, right? And kind of how big do we make the capacitors? Well, the smaller the better, right? Takes less area, for example. This tells us, careful. If you make them too small, if you make this feedback capacitor too small, you're gonna lose, right? Now, making it too big, of course, is a bad deal also, because now we have to drive this monster feedback capacitor, right? And we need extra power and current and so on for that. And in practice, there is an optimum, and you can calculate the optimum. It's relatively straightforward, right? One differential and setting the right thing to 0, and you find what the optimum is. Not too surprising, like in many of these things, the optimum is when kind of things are equal. In other words, there is not one guy that takes all the shoulders all the burden, or that takes all the cake, right? So in practice, the optimum is when you make the CGS kind of comparable to the other capacitors there. That you don't have a itty bitty little transistor and a huge sampling cap and feedback cap. That wouldn't be so good. And the other extreme also would not be good, where you have a huge capacitor, a huge CGS one there, and then itty bitty tiny feedback capacitors. You want to roughly equal. Now, having that said, sometimes you can't make them equal, because sometimes this CS or CL and so on, they're just astronomical, especially if they are somehow, there is a pad involved, right? You have to go off chip. Immediately you pick up a couple of picofarads there, or actually often more than a couple. And then you look at your transistor. Heck, I would have to make a huge transistor in order to get there, and then I have to pump a huge amount of current through that huge transistor in order to get the V star to the level that I want, right? And so sometimes you, especially now in more modern, very fast technology, you will actually have to make this one somewhat smaller than the other ones. But at least we sort of know our guidelines. We don't completely just design out of nowhere. Okay, it's getting warm again. All right. So then the other part that this equation tells us is that, okay, I mean, my noise is Kt on C. We've said that all the time, and although I guess I haven't given a proof, I don't even know how to prove this thing. I've never seen a circuit where the noise wasn't Kt on some salient C times some bunch. Of course, you can write the equation ugly, and then you don't see that anymore. But in practice, that's a good. So then, next question we may want to ask is, well, now should we worry about the noise from M2, or is it just negligible? Well, the noise contribution from M2, basically M1, got to be there, right? That's our amplifier. If we take M1 away, of course, we don't have the noise from M1 anymore, but the amplifier's gone. M2 is a little bit a different story. If we take M2 away, we have less output impedance, more Miller effect, things like that. I mean, the amplifier is still there. It's still going to work. It just has other performance that is reduced. But maybe it's still good enough. Certainly, this term here drops to 0 when we take M2 away, right? So, question then is justified to ask, well, just how much does M2 cost us in terms of noise, right? And so it costs us apparently with the ratio of Cx over Cl effective. Okay? So we want that the Cx is kind of small compared to Cl effective. Okay? So again, if we have a technology that has FTs in the gigahertz and we are running in the tens to hundreds of megahertz, that's probably feasible. If you have a technology that has an FT of 30 gigahertz and you want to build this light speed system, what is it? OC192, or no, it's another one that goes at 40 some gigahertz, right? Then that's probably not true, and this factor is big, right? Okay, so now let's use this. Let's build an amplifier based on this. Yeah. So what we want to do is we want to build a track and hold amplifier for an A to D converter. We're building a 16-bit A to D converter. Okay. And usually, especially precision A to D converters, they are preceded by something that's called a track and hold amplifier, or a SAW, or a sample and hold amplifier. Incidentally, tomorrow, you have to look at the announcement. Sorry, I just remember that. Tomorrow we have several visitors, two from ADI, and one of them, David Nern. He is giving a tutorial on A to D converters tomorrow from 2 to 3 p.m. somewhere in, maybe it's over in Soda, but check the seminar announcements. So that would be interesting, how to design A to D converters. Soda 380. Okay, thanks. Soda 380, and I think it is at this time, right? Okay, so in fast A to D converters, we have a track and hold. And why is it there? Well, because the signal here is going to change fast too, right? Otherwise, we wouldn't have a fast A to D converter. And the A to D converter, it's got to make a decision. What is the value here? What is the value here? Right? At all the sampling instances. Well, the signal's changing all the time. The A to D converter, I'm talking now really colloquially, has a hard time getting an accurate value. Right? So what we do is really we stick this into a special amplifier that's called track and hold amplifier that follows the input, and it then sort of puts out a staircase. Then our A to D converter has to convert a staircase and can do that a whole lot better. So now the trouble with this thing is that the signal here is 16 bits. Well, we want that 16 bits come out here, right? Then in terms of noise, here we have to have 16 plus bits, and here we have to have 16 plus bits, right? Because at best, our A to D converter is going to add 0 noise, but it's certainly never going to take noise away. That's already there, right? So if we want something that's 16-bit here, we better have something that's at least 16 bits here. So that means that the dynamic range here at the output of our track and hold better be commensurate with the full 16 bits. Okay? And that, we know now, 16 bits translates into 98 dB. Okay? All right, so here I wrote down a bunch of design equations. The first one is the dynamic range, and if you can use a little tad bit more zoom, okay, then everybody can read it. So, it is the it is the signal power here divided by the noise power. And the noise power we have from the equation on the previous slide, right? That's the noise from M1, that's the noise from M2, and so on, right? So that's one constraint that we certainly have to meet. Another constraint that we absolutely have to meet in our converter is that this thing has to go fast enough, and I guess I skipped a little bit on that slide. Fast enough means that the sampling frequency or application demands is 100 megahertz. 100 megahertz, 16 bits. You get a PhD out of that. If you know how to do that, then tell me, and I'll be happy to help you. I'll pay for the fab. You know, the $500,000 problem there. I'll take care of that, and you make the converter. It's good enough. Well, sampling speed's 100 megahertz. Well, what we really need to know when we design our amplifiers, well, how fast an amplifier do we need to build? We need to know the bandwidth of the amplifier. Now, there is a relationship between accuracy, clock speed, and amplifier bandwidth, and we're going to derive it. But the simplified version that's going to be good enough for this example here is shown here, where the closed-loop unity gain bandwidth of our amplifier got to be 2 pi times the sampling frequency, 100 megahertz, times a factor n, and n is the accuracy. It is the accuracy deal in here. N is the logarithm, the natural logarithm of 2 to the power b, where b is the number of bits. So it's really 16 times logarithm of 2, and that comes out to be about 10, 11, something like that. Right? So we're going to derive this. For here, it's just sort of postulated. In our track and hold amplifier, most of the time they have a gain of 1. Right? We don't want to gain up the signal. We just want to get the staircase. So the gain's 1. We, of course, are going to use our quarter micron technology. For simplicity here, we're going to make M1 and M2 the same size, so both have the same V-store. We're going to make all the capacitors, CF, CS, and CP equals CGS. We're all going to make them equal. That immediately tells us what CF is going to be, what F is going to be. Okay? Fine. So basically, we design the amplifier, figure out what the CS was, and then we make CF and CS just the same size. Straightforward. And the maximum signal amplitude is Vs. And you can then substitute here, I think in the example I use a volt later. Okay, so we have dynamic range and speed. Also from our equations before, we know that the speed, I mean, again, let's assume that the amplifier is well compensated, so that second pole, omega p, is way out there, and consequently the bandwidth is really GM over CL effective. And then I just have, these are sort of 2 simple equations that I also state here. But key is that these upper 2 that are really capturing my design objectives and so on, I got to solve those, and they now tell me what CL is, what GM is, and based on this, of course, and V star, based on this and V star, I figure out what is ID and what is W, right? Okay. So, and then I know everything for my, yes.
Because CX in some way determines my second pole, the second pole hasn't to be very away from the dominant pole, otherwise I have so why I am yes, of this ratio CX over CLF should be quite small, because the dominant pole should be, so why I'm not, because if CX is near CL, my circuit doesn't work because I have a...
then it's unstable,
yes.
a lot of extra noise.
So why I have to...
Well, the reason really is that my unity gain bandwidth here is 100 some megahertz, right? But omega p is the FT of the transistor, right? Or, I mean, it's omega t. Omega p equals omega t, and let's divide by 2 pi. So that is going to be a few gigahertz, right? So that's why I really probably do not need to worry about it. But later we are going to see. I think I have. No, I don't. I don't have them here. Later on, for something later on, I actually did simulations on this thing, and yeah, I mean, you can get extra noise from M2 precisely when this condition that FT is way out there, right? Much higher than the frequency that I'm really concerned about. Then you get extra noise. And the way I handle this is that, first of all, I mean, I've never designed a circuit that goes at 20 gigahertz or something like that. But if I did, then I would probably change my certainly change my design sort of approach and take into account a few things that now I don't need to be concerned with. And the other thing is I, of course, run SPICE, and then I see it. Well, there is this strange noise spike there. Well, where is it coming from? And track it down. But here it's kind of often it's going to be a reasonable assumption, right? And then again, it helps to make these plots that omega p is really at a high frequency. So in the bandwidth of interest here, I have really a first order roll off, right? Unfortunately, can't see it. Okay. Does this answer your question? Or?
Also, on slide 38,
48, yes.
38, yes. I redid the calculation, redone the calculation, and there is a f factor. There's 1 plus f multiplied by Cx over Cl. There is an f.
1 plus f times Cx over
yes.
Cl effective?
Yes, if you look at omega u divided by the omega p and you check the value in slide 36, there should be an f factor.
That could well be. Yeah.
Yes.
Okay, thanks. Yeah. Yeah, that's probably right because yeah, when I pull this out. Yeah. Ah, good. I used them for, I don't know, a couple of years. And I guess that's one thing I can do. I can put all sorts of mistakes. But no. Yeah, then I'll find out who thought about it. Okay, so thank you for pointing that out. So then I just plugged in numbers, and here is my 16-bit track and hold amplifier. 16 bits, 100 megasample, 1 volt, V star of 200 millivolts, 200 millivolt V star and 0.35 micron transistor. Immediately tells me what W over ID is, right? CL 400 picofarads. Earlier we said that with 1 nanofarad capacitors we can go to about 18 bits. But then we had assumed that we had a 3 volt signal. Here so a 10 times larger signal, 2 times larger capacitor, and 2 extra bits. That kind of jives, right? Because we would expect a factor of 16, right? There's a factor is 20, right? So reasonable. Coincides with what we had. We need a GM of 1.3 Siemens. This transistor is going to be big. Huge. Right? In fact, CGS is going to be 13 pico. Well, it's 10 millimeters wide, right? Possible. Yeah, you probably want to segment carefully your design, and that's one of the problems. But ID is going to be over 100 milliamps, just a lot. And notice that this doesn't include yet the fact that we are also going to get extra noise from the current source and maybe a little bit from the biasing network and auxiliary stuff and so on. So in practice, it's going to be even worse, right? So before you sign up for that 16-bit PhD, do a few more of these calculations and estimate when you graduate. Yes.
So from here, we see that 16-bit and 14-bit we compared it. We see that GM has about 16 times difference, right? Yeah, and go to the previous page, and from the formula of GM, we don't see that from there. So I wonder if there's the B is only different.
Well, maybe there is another mistake somewhere, right? What is it? We had calculated much more channel without getting into such complicated equations that if we add 1 bit, I has to go up by 4x, and GM also has to go up by 4. C has to go up by 4x consequent GM. So this result that we get a factor of 16 in between these two columns makes sense. But the formula sure says that no, it's not like that. That GM goes up for me. Yeah, so got to be something wrong, right?
Looks like it should not be linear with the bit numbers, right?
So maybe there is a square, like in this equation up there is a square. Maybe there is a square here too. I think I'm just going to make all my slides pink. They like these cartoons. You have two pictures or so. Find the error, find the difference, or something like that, right? So reality and. Okay, that's a good thing about understanding the stuff, right? In the end, it kind of doesn't matter, these little mistakes, because we know what we should be getting, and we know how to interpret the result. We can immediately say that the factor of 16 in GM makes more sense than the factor of 4 that the other equation. In fact, it's not times B. It is times 2 to the B something, right? I mean, this is definitely totally wrong times B. I mean, that would be great, right? Then maybe in square like here, right? Something like that. Yeah, I mean that's one of the problems with PowerPoint. It always looks so great that it's authoritative, right? It can't be wrong. I mean, it's nicely typeset. Oh, well, okay. So, thanks for finding these errors, and I'll try to work them out or fix them and so on. I guess there's a trade-off between actually putting complete examples with errors and not having them there with even more errors, right? So, if you find the errors, or if you
I think if you look at the unity gain frequency, there is the formula, and yes, down a little bit down. Yes, on your left. Yes, there is the formula of omega u, and you use the value of CL that you have on the right side, and you find the correct value of GM.
Yeah.
Yes, and you find that is 2. This is.
Okay. Yeah. Yeah. I think I will fix it later. This is almost like a qualifying exam. I don't know how I would do on one. So. Okay. We kind of are working on plumbing. Some of our plumbing is very fundamental, like how do we understand devices, right? And of course, noise was very fundamental plumbing that we absolutely need as circuit designers. Other things are a little bit lighter, but also important. One of the things that is a little bit lighter, but also important, is bias current sources. And all over, tail current sources, loads on amplifiers and so on. We need current sources for that. We need them for two things. We need so that we can set an accurate current. Right? We do all of our calculations with V star and everything in order to figure out how much current do we actually need for meeting our design constraints, right? And of course, we don't want to pump in more or less or whatever current, right? We want to be head on. And so for that, we want a current source that can produce an accurate amount of current. And the other thing is we want our current source to have a high output impedance. And of course, we want it to have low noise. So that's kind of summarized here. And then there is one more thing, and that is that if we have a current source, something like this, and it's made with spice, then it plain doesn't compare what the voltage is across it. It's going to pump out whatever current it should, and spice happily goes to 100,000 volts somewhere, and sometimes I get results from students who are totally spice claims in my amplifier I get 100,000 volts. Well, yeah, look at your current sources, right? But in practice, of course, we're probably going to build this something like this. That's just the most common example where we put some kind of a bias there. And then that's not exactly the case. We're going to have the right amount of current, and we're going to have a reasonably high output resistance if the voltage across here is at least some minimum value, and I call that Vmin. Okay? And obviously that immediately brings us into a quandary, right? We want this Vmin to be negative would be great, but I mean at least 0 would be a good start, right? And so we're going to look at how we choose this Vmin, and surprise, surprise, gotta do something with noise. So, and in that context, we're going to talk about a bunch of things. But let's get going on just a simple current mirror. You've seen this structure, of course, over and over. So the idea is that we build some kind of a reference current source, usually part of a band gap referencer somewhere in the corner of a chip, a guy who knows. Every big company has one guy. He has to always build the reference sources. It's kind of special, right? Yeah. So anyways, we assume that it's here and it's good. And then from then on, it's all a maze of current mirrors that replicate and distribute that bias current all over the chip. And so we have a diode-connected transistor that sort of samples the current, and then one or usually many transistors are configured as current sources. Right? Now, when we design these, often we want that the current that comes out here is exactly the current that goes in over there, and then of course we make the two transistors exactly the same size. Sometimes we want a different ratio than 1 here. So for example, in this example here, I wanted that the current here is 3 times larger than current over there. And then we do that not by mucking around with L and W or so forth transistors. We are simply going to put 3 transistors here and only 1 there, and we wire them all in parallel. Okay? If we wanted to have a factor of 1/3, in other words, the current over here 3 times smaller than the current over there, then we would put also 3 transistors, but we would put the 3 transistors here and just only 1 over there. Don't try and chop transistors in half. unless you can live with mismatches of 5, 10%. And certainly don't muck around with L, right? Hopeless to match that. There's one little thing that I just want to briefly mention here. Suppose here in this circuit here, you now need a total of 4 transistors, right? So every transistor is some kind of a box like this, right? And here is the source, and here is the drain. And of course, in order to kind of make a compact layout, a reasonable thing to do would be to lay it out something like this. Right? And then we have put all these sources together, somehow patch them together, and we also strap these 3 drains together, and there we go. We have I0 and 3 I0. Well, the trouble with this is that it doesn't work very well. I mean, it works, but we get these are also strapped together. But the trouble is that here the current is these are good for the trash can. The current, this is black. The current is flowing in opposite direction, these transistors. And experience, and don't ask me why, but experience tells me that we get mismatch on the order of a few percent if we do that. Okay? So you can't lay it out like that. Either you make one string where they're all next to one another, and then you got to worry about the resistance in connecting all these drains or sources that are miles away from each other, right? Or you would have to make it that the sources are here and the drains are there in these transistors and wire them up accordingly. Otherwise, you get systematic mismatch. Just a simple thing, but kinks your chip easily. And SPICE is not going to say anything. Okay, so that out of the way, what we're interested in now is noise. I will see shortly why we should be interested in noise. So I calculate now here the total noise current that comes out here. And well, it's not too surprising. It's kind of the same deal as before, right? There is the noise from M1 and M2. This one is M1. This is really my current source, and this is just sort of M2 is just kind of to bias it, right? The diode-connected transistor. And so I again can write the whole thing as I get noise from M1, which is really my current source, and I also get noise from M2, which is just there, so I can set up the bias curve. In practice, I probably would also get some noise from my ref, because that's also a circuit. It's got transistor, therefore noise sources, right? But I assume here that that was 0. I mean, again, I assume this because it's an example, not because it's a very good assumption. Okay, so then also what this tells me, actually, if I choose a huge ratio here, well, then I'm going to gain up the noise from M2 here with this factor of M. Okay, so sometimes, in general, we have to be careful when we make these ratios very big. All right, and then I put this result into this format here. I do as if my current source here, or current noise source here, was a resistor producing the noise, and then, of course, that resistor would have a value, right? And so I'm really modeling the noise of my current source by the equivalent current noise resistance, and that is Rn. And by comparing these two equations, I easily can figure out what is Rn. Rn is basically 1 over Gm1 times something that has to do with that ratio factor. But let's focus just on this part here. That's the more important thing. So let's not get too confused by this other factor. I mean, there's nothing very fundamental in here. But here there is something very profound and fundamental. So Rn is 1 over Gm1. Well, okay, fine. Now, first of all, in a noise current source, the noise is proportional to 1 over Rn. So for current noise, I want this Rn to be infinite, right? Really huge. 1 over Gm1 or it's not GM. Most of the time, hey, we build amplifiers. We want that GM is infinite. Now we suddenly say in the current source, we stand on our head and we say, no, GM's got to be very, very tiny, and 1 over GM's got to be large, right? So it depends. I guess if the world was divided, the world of circuit design was divided into guys that build amplifiers, the guys that build current sources, they couldn't get along at all because they would disagree on GM all the time. Okay, but now there is another resistance in our current source that is of importance, and that's the output resistance. And well, we know that this is RO in this case. This, the RO of our transistor, that's the output resistance of our current source, right? So let's put this in perspective. Well, 1 over GM, that is also equal to RO over GM-RO, and that we call AV0, right? That's the intrinsic gain of the transistor. Now, we've said that the really short channel length transistors may not have that large an intrinsic gain, but maybe we don't use the shortest channel length here. So this is maybe 50, right? So in other words, the output resistance of the current source is pretty decent, maybe, but the noise resistance is much worse. The profound thing, and I put that in red here, the profound thing is that building an active current source, a current source that made out of transistors as opposed to one that is just made out of resistors and so on, an active current source is going to boost our out. The output resistance, wonderful. If you want to have high output resistance and you don't care about noise, can do that with an active integrated circuit. Just needs a few transistors. But if you want to have low noise, not just high output impedance, then you're sunk with this approach. In fact, and we'll see that later on, when you want to have high output resistance, then low noise, then the best way to make a current source is make this the biggest resistor that you can get on your hands on, and then this is 0 volts, right? That's where your circuit lives. And you want to have a certain amount of current here, I0, and consequently the voltage here, you have to bias this at VSS equals minus I0 times R big. Right? And I just chatted with one of you, right? You work at LBL, and at LBL, one of the things that you sometimes build are particle detectors, and they measure very small currents, right? Bunch of electrons coming out. So the noise current better be very small also. So what they sometimes do is they make this really big. I mean, they open the drawer, the biggest one, 10 megohm or even higher sometimes, right? And then this thing is, don't get zapped. Okay? You can buy that. There is also medical imaging equipment or so. That's how it does it. So if you want to have low noise current source, forget about transistors. Lousy. It's a high voltage supply and big resistor. Best thing you can do. Okay. All right. So now we put this into again into context. I kind of took the punchline away, but now let's sort of go back and analyze this technically a little bit. So how should we design our current sources? Well, we have two design parameters. We have this Vmin already, and we know that if our if this lambda model and square law model and so on was accurate, then the minimum voltage that I need across my current source so that the right amount of current comes out and it has a high output resistance is VD sat. Okay? Right? Then it's in saturation. Well, now in our V star transistors, it's perhaps not exactly VD star, but sort of by analogy, I say, well, it's going to be about VD star. Let's make it K, some factor K, times V star. That is our V min, right? And experience, and later we do simulations and so on, shows that typically this K is going to be somewhere between 1 and 2, right? Then we get high output impedance. Okay, so now of course I still have the equation for my noise resistance. Forget this, just makes it complicated. And I can now substitute V star for GM, and then I end up with this expression. This should be a lowercase k, so apparently the noise resistance that I want to make large is then going to be equal to V min, which is K times V star, so let's call it V star, V min star, to remind us, divided by the current, basically, right? Well, the current's given by the application. I need a milliamp in order to run my amplifier fast enough. That leaves me only V min. If I want to have less noise, I gotta allocate more voltage to it. So that's where the 500 volt supply comes in. Sometimes low voltage is a bad deal, right? And of course, in practice, we cannot afford this extra and high voltage supply. So we're going to stay within the 3 volts or 1 volts that we have of our technology, and that means that we are going to fight. The current source designer in us and the amplifier designer in us, they're going to fight. And one wants an additional 20 millivolts, and another one doesn't want to give it, right? So on my earlier slides, I said, well, heck, that's what you get your salary for, right? That's an interesting slide here. It kind of says, well, gee, I mean, that's just because we use MOS, right? In MOS, everything's a little bit lousy, except we've got lots of lousy transistors. So that must be the reason. Let's use gas. Let's make our current source it out of germanium or something. Right? Then it ought to be better. Well, there are 2 things in here. First of all, I invite you to verify this equation. I calculate the current noise coming out of this bipolar current mirror. Bipolar current mirrors, and we said that before, usually use degeneration resistors in their emitters in order to improve the matching. And the reason is that the GM of bipolar transistors is relatively large. What is the V star of a bipolar transistor? I mean, there is no V star, but the equivalent number would be VT, which is 25 millivolts, right? Way low, right? So the GM for a given amount of current is always way high, 10 times higher than for a MOS. Maybe not quite 10 times now. That'd be biased. Only 6, right? Anyways, I calculated the noise current that comes out of here, and just be very careful. Sometimes it's easy to make the error and say, hey, look, I mean, all this noise, we have the noise current from the transistor Q1, and then we also have the noise from the transistor, from the resistor RE, and consequently, we actually, by introducing the resistor RE, we ought to be getting more noise. Well, that's not true, because not all of this noise current here actually goes to the output, because here we have really serious feedback, right? And the noise current flowing into the transistor also changes its VBE, if you want, right? And because of that, the transistor itself changes how much current comes out here. And so it's not as simple as just adding these 2 noise current sources up. But gone over how to calculate this. You got to draw the small signal model, calculate all the gains from every single noise source to the output, and then solve for I out and substitute the noise equation. That's what you get, right? So verify. Be very, very careful. Probably there is an error in this thing here, and I'm going to ask for the same thing on the midterm, and then I'm going to say, well, you are not me. I'm allowed to make errors, but not you, right? So be careful. Verify. Anyways, so instead of going, instead of looking at this complicated equation, now we can use more room, please. Instead of looking at this complicated thing and sort of getting lost with it, I said, well, gee, I mean, let me just try to understand roughly where this thing is going. And for that, I look at two extreme cases. One of them is I make GM or E equals to 0. In other words, I make or E equal to 0, and then I just have a bipolar current mirror, and the noise resistance is going to be equal to 2 over GM. It was 1 over GM for the MOS. It was gamma over GM, right? 1 over gamma times 1 over GM. And so here, and then in the end, I can again sort of go to this V min or V star, and so I still find Rn is for the bipolar current mirror still Vt is the bipolar's V star, right? Divided by IC. So the bipolar actually is worse than the MOS, and it's simply because the bipolar is more efficient, so it produces more GM, which is normally a good thing, but not when we build a current source, a DC constant current source. Then GM is a disaster. It adds noise, right? Okay, so no, the bipolar isn't gonna be the solution. Now I don't know enough about gas, but you can go and study the literature and see whether you come to a different conclusion. And then the other extreme, I said, well, I make GM or E huge. So at that point, it's really sort of the or E that now determines the gain. Right? Then this thing. Interesting enough, if my GM or E, if I make that big, the noise from the BJT becomes irrelevant. And I only get noise from RE at that point. Okay, so apparently GM-RE is sort of like a knob that allows me to choose noise from the transistor or noise from RE and the right mixer. So unfortunately, they all have the same flavor. Otherwise, that would be neat. Huh? So then I get this RE, and arguably this second term here is about 1. So Rn is equal to Re at that point, if I make this really very large, and it is equal to, and consequently that's equal to V min, the voltage across Re, divided by IC. Doesn't help at all. It's exactly the same thing. Bipolar and MOS is exactly the same thing, except that in bipolar, you absolutely got to introduce these resistors here, not only for matching, as we already knew, but also in order to deal with the noise of that monstrous GM bipolar transistor. That is a big disadvantage here. Right? So, well, and I compare it to the MOS, right? In either case, it's V min divided by I. That's how much noise we get. Low noise, large V min. All right. Any questions? So nobody fell asleep. I guess that's working, for me at least.